All right, class. Welcome to the first lesson of Chapter 7. Before we had, before this lesson, we actually had introduced what we called sampling techniques. And again, the idea of sampling techniques was that you can use that to get information about a population taken from a sample using various techniques. So what we're going to be doing is we're going to kind of go off of that and talk about how we actually get information from these samples. So we're going to introduce what we call confidence intervals in order to study a given population. And what do we want to study about the population? In this lesson, we actually want to study the mean of the population. So that's the parameter that we want to estimate. So the goal of the lesson is to essentially be able to determine the confidence interval for the mean of a population, assuming that we know the standard deviation. And obviously we're going to talk about what a confidence interval is, and we're going to talk about ways that we can estimate a parameter. So let's get started. So we're going to talk about the two different types of stats, essentially, two branches, if you will. The first branch is descriptive statistics, and this branch is aimed at essentially summarizing or describing a sample. So when you take a sample, you want to be able to describe it or summarize a sample. So such as, being able to find the mean of that sample, measures of central tendency, mode, measures of spread, etc. And we've done this a lot when I give you a whole bunch of data and ask you to get information about it. So we've done this quite a bit in the course. The next thing which we are actually going to introduce in this course is inferential statistics. So inferential statistics basically uses the sample to learn about the population. So our goal is to learn about the population or to infer characteristics about a population given the sample. So that's why it's called inferential statistics, because you're inferring the characteristic of the population based on the sample. So one aspect of inferential statistics is estimation. So what we do is we obtain a sample and we use that to estimate the parameter. So the idea is that you want to estimate the value of a parameter from information obtained from a sample. So for example, consumers spent an average of $126 for Valentine's Day this year. So this data was collected from a sample, and then they used the average from the sample in order to infer that the population as a whole spent an average of $126 on Valentine's Day. So this is an example of inferential statistics. So they didn't literally, spend time and actually find every single person and track them down to figure out what the average is. They inferred it from a sample. Since the populations from which these values were obtained are large, these values only represent estimates of the true parameters and are derived from data collected from samples. Essentially what we want to do is we want to estimate the population mean or infer what its value is, or the variance or the standard deviation from samples. So that's the premise of statistics as a whole. So inferential statistical techniques have assumptions that must be met. So there are about 3 assumptions that we'll look at. So first off, the samples have to be randomly selected. And we kind of talked about this when we talked about random sampling and different types of sampling techniques. Randomness is how you want to select your samples so that everyone is equally represented. Either the sample size must be greater than or equal to 30. This is the second condition, that you want a large enough sample size. So if it's either greater than or equal to 30, or the population must start out being normally distributed if the sample size is less than 30. So you either have a sample size bigger than 30 and the population is not normal, or you have a population that's normal and the sample size is less than 30. Alright, so point estimates and estimators. So there is a type of estimation known as point estimation, and essentially what that is you're estimating given what the value is given one point or one value. Alright, so one of the main goals is to use sample measures which we call statistics. So the statistic is the measure obtained from a sample, and the parameter is the measure obtained from the population. So we want to use statistics to estimate parameters. So a point estimate is a specific numerical value estimate of a parameter. The best point estimate of the population mu is actually the sample mean, which is x bar. Alright, so essentially, let me kind of repeat what I said. The point estimate is basically when you use one value to be able to estimate another value. So in this case, we're using the sample mean x bar to estimate the population mean mu. Alright, so for example, suppose a college president wishes to estimate the average age of students attending classes this semester. The president could select a random sample of 100 students and find the average age of these students is 22.3 years. So what the president is going to do is, I'm going to take this value, this 22.3 years, which is my sample mean, and I'm going to use that to infer that the average age of all the students in the population is that number, 22.3. And that's known as a point estimate. When you use a sample measure to estimate the population measure, we call these statistics estimators. So we just use a point estimator. How do we know what a good estimator is? Well, a good estimator has to have certain properties, all right? So the first property is the estimator has to be unbiased. Unbiased means essentially that there is no, it's not biased by anything in the sample. So it's not, so the number isn't changed and is due to randomness, okay? So the number is completely unbiased due to randomness. So which means that on average, if you were to average the estimates, this means that the average or the mean of the estimates is equal to the parameter being estimated. So essentially what that means is that since the value is completely random, that means that it'll change a little bit. It might change, so for example, let's say the population mean is 5 and you obtain a sample, x bar, and you got about 4.7. So so if this is completely random, it should be a little bit off, and it should be a little bit it should always be a little bit off from the original population, right? So if you took another sample, let's say you got 5.3. Another sample, let's say you got 5.1. Then you got 4.9. So on average, if you were to average these guys, right, some of the errors in these should cancel out, so that when you take the average of these guys, you would get approximately the population mean. Okay, so basically the errors that you would get would kind of cancel each other out when you average them. And that's what really makes a good estimator, and that's what makes it unbiased. Also, the estimator should be consistent. What we mean by that is, as you increase the sample size, these numbers should be approaching the mu. So like, if I have a small sample size, right, let's say I have a small sample size of like 2. Well, 2 is not a very good sample size, but if I took the average of that, let's say I get 3. If I increase the sample size, if I increase the n, then my x bar should be getting closer and closer to that mu. And that's what consistent means, is that as you increase that sample size, you get closer to that actual population mean. It also has to be efficient. So efficient means that you have a very small spread. So you have the smallest variance or spread. Again, what that means is that if I were to take the average of a sample, the averages should be very, very close to each other. They should not be that far off. So like 4.8, 4.7, 5.1, they should be relatively close to each other, and there should be minimal spread. And that has to do with being consistent and efficient. So if I were to take another average and I got like 2, well, that's not very efficient because of the spread is very large here. Okay, so that's what we mean by good estimators. All right, so now let's look at the idea of confidence intervals. Okay, so confidence intervals. So this basically, so we talked about point estimators. Now we're going to talk about interval estimators or interval estimates. So the sample mean, whenever you collect a sample, the sample mean will always be different from the population, right? In some way. It could be bigger than the population mean, it could be smaller than the population mean, or in rare instances be actually equal to population mean. But in general, it'll be different because you're taking it from a sample and not from the population. And this error is known as a sampling error. We mentioned this in another lesson in the previous unit. But this is called a sampling error. And the idea is, for a good estimator, the sampling error has to be as small as possible. The only problem with point estimates is that there is no way of knowing how close we are to the population mean. So like if you're trying to estimate, the population, and the population mean is 5, for instance, right? And let's say you get a sample and you get 3. You have no way of knowing how close you are to the actual mean, because in reality, you can never really know what the mean is, the population mean is, until you sample every single person in that population. So if I have like 3, that doesn't really tell me how close it is to it. So because of this, what we do is we use another type of estimate, which is called an interval estimate. And this basically is an interval or range of values. So it's a range of values used to estimate the parameter. So sometimes the interval contains the parameter, sometimes it doesn't. That's why it's known as an estimate. So for example, let's say you wanted to find the average age of all the students that might be between 21.9 and 22.7 years. Okay, so let's say you want to estimate the average age of those students. And so that's your interval estimate. So mu is between 21.9 and 22.7. That's what your guess is. There are a couple ways that you can write this. You can write it like this. That's one way of writing it. That's way number 2, and that's way number 3. Okay, so your guess is that the mean is somewhere between those two numbers. We don't know if it's actually between those two numbers, but we're getting a good guess that the mean is between those two numbers. So this is just an estimate. So notice we have more numbers that are actually in this estimate because it's an interval, and therefore we have a greater chance of actually selecting the mu. So we have a greater chance of actually containing the mu within this interval than we would if it was a point estimate. So as we said earlier, the interval estimate may or may not have the population parameter, which is why we assign a degree of confidence called the confidence level. This tells us how confident we are in the estimate that we provided. Okay, so for instance, you may choose to be 95% confident that the interval has the true population mean. So that's known as a 95% confidence interval. If you wish to be 99% confident, then what you would have to do is you would have to make your interval larger. So you'd have to make your interval wider, and this will make you more confident in the estimate. So for example, if instead of doing between 21.9 and 22.7, if you wanted to be 99% confident, you might increase this to like 20, from 20 to like 24 or something like that. So you're going to make your interval wider to ensure that you have a greater chance of having the mean in that interval, if that makes sense. So the confidence level of an interval estimate of a parameter is the probability that your interval will contain the parameter, assuming that enough samples are selected. Alright, so if you did a 95% confidence interval, then there's a 95% chance that your interval has the parameter in it, and there's a 5% chance that it does not. If you want to increase the chances, then you need to make the interval wider to ensure that you have a greater chance that you have your mean in that interval. A confidence interval is a specific interval estimate of a parameter determined by data obtained from a sample and by using the specific confidence level of the estimate. Common confidence intervals used in statistics are 90%, 95%, and 99%. So those are three of the most common confidence intervals, although there are other ones that you can use. The formula for the confidence interval is given below. Okay, so this right here these are three different ways of expressing the confidence interval. All right, so in this case, the alpha, the Greek letter alpha, represents the confidence level. So the confidence level, actually this should say the 1 minus alpha, so technically speaking, 1 minus alpha represents the confidence level. So alpha is basically the total the area in both tails. So for example, if you wanted like a 95% confidence interval, right? So you want the area in both tails here. So you have to have a cutoff. So let's say this is 2.5%, and then this is 2.5%. So then your alpha is 5% or 0.05. And your 1 minus alpha is 95%. That's your confidence level. So 1 minus alpha is your confidence level. So 95% confidence. But your alpha is 0.05. Okay. Hope that kind of makes sense. But we'll do more with this. So the confidence level, like we said, is given by the 1 minus alpha. Okay. So how do we know what the z alpha over 2 is, right? So for a 90% confidence interval, you're going to use z alpha over 2 is 0.1.65. For 95%, you're going to use 1.96. For a 99% confidence interval, you're going to use 2.58. So we know what our x bar is from the data. Now we know what z alpha over 2 is. And we know what standard deviation is. We know the sample size. So we can plug it into this formula and get a confidence interval. The z alpha over 2 is known as the critical value, and the term that you're adding or subtracting to both sides, so this term, the z alpha over 2 sigma over square root of n, is called the margin of error. So the margin of error is the maximum likely difference between the sample estimate of a parameter and the actual value of the parameter. So how do we interpret the confidence interval? So let's say we had a 95% confidence interval. Then there is a 95% probability that your interval contains mu. So how do we get these z alpha over 2s? So how do we get those? So I'll show you how to I'll show you how to get that, and I'll show you how to come up with the confidence interval formula. So it turns out that the confidence interval formula that we see up here actually comes from one of our previous formulas. And I'll write down that formula. So it actually comes from this formula right here. Right here. Do you remember this formula? So this is the confidence, or this is the central limit theorem formula. So the idea is that you're trying to use the x bar average, right, to estimate the mu, the parameter. So what you're going to use is you're going to use the x bar formula. And then what you're going to do is you're going to solve for x bar here. All right, so we're going to go ahead and solve for x bar by multiplying the sigma over square root of n. Actually, we're trying to solve for mu here because we want to figure out what mu is. So we're going to solve for mu. So we're going to get rid of the sigma over square root of n by multiplying both sides by that. So now these cancel. So now you have z sigma over square root of n equals x bar minus mu. So we want to solve for mu, right? So what I'm going to do is I'm going to I'm just going to add mu to the other side. So I'm going to add mu to this side. And then I'm going to subtract this over to the other side. All right. Now notice that we have mu is equal to this, right? Remember that the z can actually be positive or negative. So since the z can be positive or negative, I'm going to write a plus or minus here. Because if z is negative, it becomes plus. If z is positive, it becomes negative. So this becomes an interval now because z can be positive and negative. So now I have mu is x bar plus or minus z sigma over square root of n. So now this tells me that mu can be between the positive version and the negative version. All right, and this is our derivation of the confidence interval. Okay, so that's where that confidence interval formula actually comes from. And then we're going to change z obviously to z alpha over 2. But that's where that formula comes from. How do we get the z alpha over 2 though? So it's actually quite simple. What you want to do is you want to so if 95% is my confidence level, then that means alpha is 5%. Okay, so alpha is 1 minus 95%, 1 minus the confidence level. So that's my alpha. And then what I do is I take the alpha and I divide it by 2. And that's why we have the alpha over 2 in the z. And then that represents 0.025. What that's saying is that I want this to be in both tails. So I'm going to draw a bell curve, and in both tails I have 2.5%. So this is 0.025, and this is 0.025, which make a total of 5%, which is my alpha. All right, so each of these is equal to my alpha over 2. So what we want to do is figure out what the z alpha over 2 is, that's why we use that symbol. So now we know we can find the z alpha over 2. Well, how do we do it? Well, we know that this is 0.025, so we can look that up on the z chart. All right, so I'm going to go ahead and pull my z chart out and look up the area of 0.025. All right, so let's go to the z chart. And we need an area of 0.025. So the closest area to that, there it is, 0.025. That's my area. So that means my z is negative 1.96. So negative 1.96. I don't know if you guys were able to see that, negative 1.96 right there. And that would be 0.025, okay? So negative 1.96. So that means my z alpha is both positive and negative 0.96. So z alpha over 2 is plus or minus 1.96. All right, which explains, so that's your z. So that's how we got the 1.96 here. All right, and that's why we get the plus or minus version. So you could just use 1.96 because the formula already has both the positive and the negative version. That's how we get the z alpha over 2. So this this illustration kind of shows you what we're talking about when we're doing an confidence interval. So when we're doing a confidence interval, right, the population mean is in the middle. What we're trying to do is estimate that population mean using the bell curve and using a confidence interval of 95%, which means that there's 5%, or there's 2.5% in each tail, right? Just like we showed you earlier. So there's a 95% chance that we have the population mean in between these two numbers. All right, what are these two? So what is this? This called, this right here is the error. So this is the margin of error. Okay, so this is the error from the estimate. So the margin of error is, each of these halves of the intervals. And the margin of error is given by, these terms. So margin of error. All right. So again, if you increase the confidence level to 99%, well then you're going to increase the margin of error, right? The only way that you can increase the confidence level is if you increase the margin of error and made the interval larger. So yes, you're more likely to contain the mean, but you also have a larger margin of error. So there's a trade-off here. And in order to get this, you're going to need a larger sample size. So there's always pros and cons to the higher confidence level as opposed to the lower confidence level. All right, so there's a trade-off here that you have to choose. So this is why we generally choose 90, 95, and sometimes 99 on certain cases. All right, so what are our assumptions for using the confidence interval? So you can only use a confidence interval if you follow the requirements, right? So the sample has to be random, and you have to either have greater sample size bigger than 30 or equal to 30, or it has to be normally distributed if you have less than 30. So let's look at an example to see how this works. All right, so it says a researcher wishes to estimate the number of days it takes an automobile dealer to sell a Chevrolet Aveo. A random sample of 50 cars had a mean time on the dealer's lot of 54 days. Assume the population standard deviation to be 6 days. Find the best point estimate of the population mean and the 95% confidence interval of the population mean. Okay, so we're going to look at the point estimate first. But let's list out what we have here. So we have a random sample of 50 cars. We have a mean time of 54 days. So they said that the random sample had a mean time of 54 days. And they give us the population standard deviation to be 6 days. So our point estimate is going to be given by our average, our sample average. So the point estimate of mu is 54. So we're saying that mu is approximately 54 because that is our x bar. All right, so that's the only gauge that we have to estimate the mu, 54. Now if we want to do an interval estimate, right, then we're going to do the 95% confidence interval. So what we're going to do is we're going to use the formula for the confidence interval, all right, which is x bar plus or minus z alpha over 2 sigma over square root of n. So we're going to calculate those numbers. So x bar is 54 plus or minus z alpha over 2 for a 95% confidence interval. Remember, we established that the z alpha over 2 is 1.96. So we're going to use that number here. And we know that the sigma is 6 days, and the square root of n is 50. So we got n is 50, so we got square root of 50. So we got two numbers here. We got to do the plus version and the minus version. All right, so we got two answers here. So let's do the minus version. We're going to do 54 minus this first on the calculator. All right, so 54 minus that. So 54 minus 1.96 times 6 over square root of 50. So I have 52.34. Now I'm going to calculate the plus version of it by doing 54 plus 1.96 times 6 over square root of 50. And I get 55.66. So that is my confidence interval. My confidence interval, my 95% confidence interval, is between 52.34 and 55.66. So I'm using this interval to estimate what I think the population average is for the Chevrolet Aveo. All right? So I'm thinking that the mean is between those numbers, and I'm 95% confident in that, which means that if I keep doing samples, 95% of the time the mean is going to be in those confidence intervals, in that confidence interval. Okay, so let's look at another example then. A large department store found that it averages 362 customers per hour. Assume the standard deviation is 29.6 and a random sample of 40 hours was used to determine the average. Find the 99% confidence interval of the population mean. So we know that we average 362 customers per hour based off of a sample taken. It says that assume that the standard deviation is that 29.6, and assume that we have a random sample of 40 hours. So they actually took the sample, and that was 40 hours. Okay. All right. So all right. So we got the n, we got everything else that we need. So we're going to find a 99% confidence interval. So for 99% confidence interval, this means my z alpha over 2, right, is going to be, so we're going to look at the 99% confidence interval. If you look over here, the 99% confidence interval, the z is 2.58. All right, so we got 2.58. And again, to derive that, you can do a bell curve. So 1 minus 0.99 is 0.01, and then half of 0.01 is 0.005. So that's on each side. And then you look up the area for 0.005 on the z table. .005, which if you look is about is about 2.58. So if you look at it, negative 2.58 and positive 2.58. So that's how we got this number here. All right, and it's plus or minus. All right, so now we're going to do the formula. So the formula for the confidence interval is x bar plus or minus z times sigma over square root of n. All right, so we're going to do the plus or minus version and get that answer. So if you did the negative version, you get 349.93, and if you did the positive version, you get 374.07. All right, and that is your confidence interval. So we're 99% confident, so 99% of the time we're going to have a mean. If we keep taking samples and stuff, we're going to get a mean between those numbers. So the population mean is going to be between in that interval. All right. So now we're going to look at how we determine the sample size. So sometimes you're doing a study and you want to determine what's the minimum sample size that I need to be able to approximate, the population mean. So what's that minimum sample size that I need? So how do we find that? Well, in order to find that, we need to know a few things. So we need to know the margin of error. So how close to the true mean do you want to be? Do you want it to be within half of a unit? Do you want it to be within 2 units, 5 units? What's your tolerance for that? What's your error? You have to know what your standard deviation is. So like, what is the spread of the data? And you have to know the degree of confidence. How confident do you wish to be? 90%, 99%, 95%. So you have to know those 3 things, and that'll help you determine the minimum sample size that you need for your experiment to be able to estimate the population mean. All right, so this is the formula for the minimum sample size, and it's actually quite an easy formula to actually obtain. So you can get this formula actually from the normal formula that we did before, the confidence interval formula. So I'll show you how to do that in a second. All right, so let's show you how to get that formula. So remember that the confidence interval formula was x bar plus or minus z alpha over 2 sigma over square root of n. So what we do is we determine what our tolerance is. Okay, so what is our tolerance for the error? So we're going to look at the margin of error here. We're going to call that E for margin of error. All right. So that's going to be called E. So we got to figure out what is our minimum sample size so that we can get a certain error. So we're going to set E equal to that, and then we're going to solve for n. So when we solve for n, I'm going to multiply by square root of n on both sides so that I can move it over. So I have square root of n E equals z alpha over 2 times sigma. Then I can divide off the E. And then I'm going to solve for square root of n by squaring both sides, get rid of that square root, and that's how we get the formula for n. All right, so that's the derivation of the sample size formula. You don't have to know that derivation, but I wanted to show you so that you know where it comes from. These formulas ultimately come from the same source, right? So let's say we have a scientist wishing to estimate the average depth of a river. He wants to be 99% confident that the estimate is accurate within 2 feet. From a previous study, the standard deviation of the depths was measured to be 4.33 feet. So we know that the standard deviation is about that much. We also know that we want to be accurate within 2 feet. So that's our tolerance. That's our margin of error. And we know that we want to be 99% confident. So we know that since we want to be 99%, we want to do a 99% confidence interval. So we need our z alpha over 2, which we said was 2.58. If we go back, it was 2.58 for a confidence interval of 99%. Right there, 2.58. All right, so now we can go ahead and begin to calculate this. So we have n equals, so we have the z alpha over 2 sigma over E squared. So we have 2.58. Our sigma is 4.33, E is 2, and then square it. Alright, so we're going to go ahead and get the number on the calculator. And I get about, so I've got approximately 31.2. All right, so since we got a value of 31.2, we're gonna round this up. So we're gonna round up to 32. So round up. And the reason why we round up is because this, remember, 31.2 is the minimum sample size we need to have a tolerance level of 2. So that means that we can't go below 31.2. And we can't have a decimal for sample size. That doesn't make any sense. So we're going to bump it up to 32. So 32 is the minimum sample size that we need in order to make this happen. So again, keep in mind that if you want a 99% confidence interval, then you need a larger, if you want to go from 95% confidence interval to 99%, you need to compensate that by increasing the sample size. So that means you need larger samples. So there's always a trade-off with these things, okay? So when you design an experiment, sometimes you have to keep these in mind. Alright guys, so that's it for the lesson. There's a lot of conceptual stuff in it, but the calculations themselves are actually relatively simple. So I hope you guys got the lesson, and good luck guys.